This is FRQ 5-2. A 20 kilogram box on a horizontal frictionless surface is moving to the right at a speed of 4 meters per second. The box hits and remains attached to one end of a spring of negligible mass whose other end is attached to a wall. As a result, the spring compresses a maximum distance of 0.5 meters, and the box then oscillates back and forth. Part A, number 1, says the spring does work on the box from the moment the box first hits the spring to the moment the spring first reaches its maximum compression. Indicate whether the work done by the spring is positive, negative, or zero. And then part 2 asks you to justify that. So the answer, part 2 asks for the amount of work. Never mind. Part 1, the answer is negative, right? The work done by the spring on the box is negative. There's a couple of ways you can explain that. First of all, you could say the box is moving to the right. It doesn't really say which direction it's moving, but you can say the box is moving in one direction. The spring exerts a force opposite to the direction that the box is moving. Therefore, the work done is negative by FD cosine theta. Our theta is 180. So that's one way you could do it. You could also use the work energy approach and say that since the change in kinetic energy was negative because the speed slowed down, you could say it's negative that way. So either way there, 1 point for saying it's negative and 1 point for a justification. Now, sorry, this is not part B, it's part 2 of A. I don't know why they do this. Part 2 says calculate the magnitude of the work. So in order to find the work done by the spring, we have to know the spring constant, and we don't. But what I do know is the change in kinetic energy. So the initial kinetic energy is half mv squared, right? So 1/2, the box is 20 kilos, and the initial speed is 4 meters per second. And then we square that, and so we get 160 joules. So even though we don't really know much about the spring, we could calculate the change in kinetic energy. And remember, they're always going to do that. They're going to ask you to calculate something, and you're going to say, I don't have enough information to calculate that. So where you need to go next is, what do I know that's equal to what they're looking for that I could calculate? Okay, so I said, I can't calculate the work. I don't know enough about the problem. But what's equal to work? Oh, work's equal to the change in energy, and I can calculate that. So I think we've done that a few times, and hopefully it's starting to get a little bit easier for you. Part B says to calculate the spring constant, okay? Now we know that the maximum energy held by this system is 160 joules because we just calculated that in part B. And so I also know that that's equal to 1/2 Ka squared, all right, where A is the maximum distance that's compressed. And we know that A is equal to 0.50 meters. So I can calculate K is 2 times 160 joules over A squared, and I get 1280 newtons per meter is my spring constant. So 1 point for conservation of energy, 1 point for the substitution of values from part 1 gives you 2 points for this. And it has dawned on me that I didn't tell you the rubric for these two parts. For part A1, you get 1 point for saying that it's negative and 1 point for a justification. For part 2, you get 1 point for the relationship between work and kinetic energy, 1 point for substituting the values correctly, and 1 point for the answer. So we got 5 points for part A, 3 points for part B, and now we're on to part C. So C asks us to find the maximum acceleration of the box. And we know acceleration is not constant while a spring mass system is oscillating, okay? But we know by Hooke's law that the magnitude of the force is equal to K times X, and then by Newton's second law, that's equal to F equals ma. And we're not really worried about directions at this point. So I can find the acceleration by Kx over m, substituting the values that I have from previous parts and from the information given, we find that the acceleration is 32 meters per second squared. Okay, rubric, 1 point for relating acceleration to k and x and m, that's this, okay? Then 1 point for our substitution from part B, and then we get our answer. So if your answer from part B was wrong, but you substituted it here, you can get these 2 points, all right? So never, ever, ever give up, okay? If it's part B and you can't for the life of you figure this out, then you write something like, I tried to find the spring constant, I can't figure it out. Let's say it's 500 newtons per meter. Then you go on, you can still get all those points. I know it's really disheartening, but I promise you can get a few extra points that way. Okay, so part D is going to ask for the frequency of oscillation. Now, I don't have a formula for that, but I do have a formula for the period, 2 pi rad m over k. That formula is on your formula sheet. Make sure you can find it when you need it, okay? I get 0.785 seconds. The frequency is 1 over the period. That gives me 1.3 hertz, right? Rubric there, 1 point for a correct expression for F. Like 1 over t, okay, so a point there, and then 1 point for correct substitution. Okay, on to step E. All right, this is part A. I apologize, this is a mess, but I've been working on it for like 5 minutes, and I tried to make a nice graph, it didn't work. Part E says, on the axes below, sketch the kinetic energy K of the oscillating box as a function of x, the position x for the range minus 0.5 to positive 0.5. So we know that essentially we're graphing the speed of this, right? Because the mass isn't going to change. We know that the speed is 0 at both ends and it's highest in the middle. So here's my graph. I tried to make a circle. It didn't work. So this is what's important, is that we've got a graph that we have 2 points for this graph. 1 point for a positive k everywhere and a k equals 0 at the end points. Then we get 1 point for a smooth curve that's concave down. So I don't know how else you might have done this. I don't know how else to get from negative 0.50 to positive, then go like this. But 1 point for a smooth curve concave down. Part E2 asks you to sketch the acceleration of the block as a function of position x from negative 0.5 to positive 0.5. So this is what the graph looks like. This is for E part 2, okay? When it's far, the acceleration has this, it starts as positive, it's 0 for an instant, right, when the block is at equilibrium, and then when the block is all the way out, then the acceleration is negative. So keep in mind Hooke's law, okay? There's that negative sign in there. In fact, this is what they give you, right, on the formula sheet. That's fine, but you got to think of Hooke's law like this. If x is positive, the force, I shouldn't put a plus. We're not doing factor of change. If the displacement is positive, the force is negative. And if the displacement is negative, the force is positive. And because the acceleration is just the force over the mass, the acceleration has that sign as well. So when we start off with the position negative, our acceleration is positive. When our position is positive, our acceleration is negative. So 1 point there for a straight line, negative slope passing through the origin. Yeah, make sure you pass through the origin, because when the block's at equilibrium, there's no force and therefore no acceleration. So 3 points for part E. Now, there was this random 1 point tacked on. It said, if you have correct units on 3 of the 4 calculated answers, you get an extra point. So where are the calculated answers? Here's 1, the frequency. Here's 2, the acceleration. Here's 3, the spring constant. Oh, here's 4, the actual work done. So those are the 4. If you have the correct units on those, they throw you an extra point. So don't ever tell me that units aren't worth anything. Okay, that's it for problem 2.